really useful, and we're going to use it a lot. Not just that it's not a difficult situation to understand. We don't have to wait till chapter 4 for this. It's called L'Hopital Rule. L'Hopital. French. L'Hopital or L'Hopital's rule. It is applicable only in 2 situations. Out of 7 indeterminate cases, only in 2. In 0 over 0 or infinity over infinity. So here's the situation. If we have limit of 2 functions, p over q, as x approaches a. In these situations only, you can determine the limit differentiating the top by itself and differentiating the bottom by itself. We never differentiate a quotient like that. And this is not a quotient to be seen as a quotient that we need to differentiate. No. This mathematician showed that if you want to determine the limit of p over q, whatever, and the situation is either 0 over 0 or infinity over infinity, only in those 2 situations you are allowed to consider differentiating the top by itself and the bottom by itself, and that will give us the answer, the final answer. So let me just make up an example because it's not in this chapter, because we're going to use this in a minute. So let's say limit as x approaches 2 from x squared minus 4x plus 4 over x squared plus 3x plus 2. Minus 3x plus 2. Of course, I want x minus 2 in the denominator, so x minus 2 times x minus 1. Okay. So what is the top? Where is the top going to? Of course, 0 over 0. Excellent. Good. So which factor do you expect to go away? All right, but that's not what we want to do. This is what we've been doing so far. Since it's 0 over 0, since it's a function over another function, I can use L'Hopital's rule. By simply differentiating, we couldn't do this in chapter 2, right? Because we didn't know derivatives. So now limit as x approaches 2 and differentiate the top disregarding the denominator. Good. Differentiate the denominator as if the numerator doesn't exist. Very good. And now let's try again. The top goes to, yes, and the bottom goes to. So the answer is, that's it, 0 over 1. Right? 2 times 2 is 4, 4 minus 4 is 0. 2 times 2 is 4, 4 minus 3 is 1. 0 over 1 is 0. Quite elegant. Quite elegant. Okay? We could not use it before. We're going to use it in a minute, but not before we go through derivatives of trig functions. 3.3. Yes, please.
So the derivative of negative 4x, it would just be 4 and x is dropped.
What is the rate of change of 4? So you have $4 in your pocket. What is the rate of change of 4?
0. Not 4x, x is
What is the derivative of x?
1.
How much is 1 times 4? Better? Derivatives of trig functions. Ready? In the past, I will always ask my students to say which derivative they want me to show. Either the derivative of sine or the derivative of cosine. And if you choose, let's say, cosine, I go through the entire proof showing that f prime of x, which is the limit as age approaches 0 from cosine x plus age minus cosine x divided by age is such and such. I can show you the process. It's a long process. I'm not going to ask you to it. We can do this sometime when we have time. We can go back to it. So the derivative of cosine x, it requires a lot of trig identities. After class, if you are curious, we can sit down and I'll show you the proof of any sine or cosine. So the answer is negative sine x. So sine x prime is cosine x, and cosine x prime is negative sine x. We can prove after class when we finish today, if you'd like, either one. If you're interested, we can do that. It's a long sequence of trig identities. So we can simplify this as much as possible, and we get that. Okay, when age approaches 0. Now, let's suppose we would like to determine the tangent prime. Well, tangent prime, first of all, tangent is a ratio of sine x over cosine x. And since it's a ratio, we'll have to use the quotient rule. Can anyone dictate the quotient rule for tangent? Top prime, very good, times the denominator, minus the top times the denominator prime, but since it's negative, I'm going to change this into positive, over the denominator squared. But we do know a basic identity from trig that cosine, it tells us that cosine squared plus sine squared is 1. So this is nothing else but 1 over cosine squared x. But we also know that there is a trig function that is 1 over cosine. If it starts with c, it's secant. If it starts with s, 1 over sine squared, it would be cosecant. So 1 over cosine squared is secant squared x. So now we have to add this to our list of derivatives. So one more time, sine x prime is cosine x. Cosine x prime is negative sine x. Tangent x prime is secant squared x. Cotangent prime is negative cosecant squared x. And we do have, of course, secant prime and cosecant prime. Secant prime is secant tangent. And of course, cosecant will be negative cosecant cotangent. Yes, we have to add these to the arsenal of functions that are the derivatives of important functions, like the square root of x. Yes, like polynomial. Yes. Is cosine squared, and cosine squared plus sine squared is 1. That's let me write that for everyone. Thank you for reminding me. So sine squared of an angle plus cosine squared of the same angle is 1. This is one of the basic trig identities, from which we develop a lot of other ones. Okay, so now we are finally ready to work on this. Limit from sine x over x as x approaches 0. We've seen this before. We looked at it with a graph, with a graphing calculator, and that reminds me, I shed a tear or two when I saw something like this. So if you did something like this, make yourself a note. Something like, I'll never do this again. I cannot remove the argument inside a function with something outside and get sign. Sign does not exist without an argument. So if you did this, just remember you broke my heart. So cross it out and then write down somewhere, I will never do this again. Okay, so what is the answer here?
1.
Okay, it is because we looked at the graph. Now, sine x, when x is 0, where does sine go?
0.
Perfect. And where does this go? Excellent. Good. So now I have another tool that I just learned that if it's a function over another function, and the situation, the undeterminate case is 0 over 0 or infinity over infinity, only one or the other, then I can use what it's called L'Hopital's rule. So this is limit as x approaches 0. What did we say the derivative of sine equal to? Very good. What is the derivative of x? And now please tell me what is this answer. How much is cosine 0? 1. And we did not need any graph. Good. Now let's look at a few examples. Please choose anything you want. I'll tell you where they are. So we are on page 197. Anything from 1 through 16 if you'd like to choose. And then we look at those limits. If you don't want to pick, I will. There is no escape. Okay, I will. Thank you for the vote of confidence. I am going to pick 12 on 197. So we have y equals cosine x over 1 minus sine x. Okay, so they're asking us to find dy over dx. Ready? So then dy over dx equals. Remember, this is a quotient. You can already, if you'd like, write 1 minus sine x everything squared in the denominator. You can do that. So now we differentiate using the quotient rule. The top function prime. Excellent. Times the denominator. Minus the top function times the denominator prime. What is the derivative of 1? 0. What is the derivative of sine? With minus in front. So I have minus cosine times negative cosine. So I will put plus times cosine. If you attempt to simplify something like this, that will be a terrible mistake, right? So we distribute now. Negative sine x plus sine x but squared plus cosine squared x over 1 minus sine x squared. As we remember, when I refreshed the memory on sine squared plus cosine squared, what would that be?
1.
Very good. I'm going to put it, although you know I don't like negative leading coefficients and not descending, whatever, but I'm going to write it like this time because I peeked to the denominator and I see something very interesting. Now I can simplify because I simplify a factor. The whole thing with one of those from the denominator. What is left at the top? Remember, you always have to write 1, not to write 0, because I've seen it. So this is 1 over 1 minus sine x. And that's fully simplified. Any questions on the process? Anything? Any questions on the yes, please, Vanessa. Go.
Can you just like reduce or like the top one, the one
Yes.
above it?
You mean here?
No, the one, that one. How did you get there?
So negative sine x times 1. Negative sine x times negative sine x. And cosine times cosine.
I understand that, but how did you get to the next step?
This is 1. Sine squared plus cosine squared is 1.
Oh, okay.
1 minus sine x. Very good. Let's look at, do you have a preference? Okay, let's look at 8. Cotangent t over e to t. Cotangent t over e to t. Stop me if you have questions. So the same idea, dy over dx, it's still a quotient, cotangent at the top, e to the x at the bottom. This is a nice function, right? Good. So you can already write the denominator if you'd like to. E to t squared will be e to 2t, or you can write it as e to t squared. It's up to you. Copy the base, multiply the exponent. Okay, what do we have at the top? Cotangent t prime. That's negative cosecant squared t. Excellent. Times the denominator. Minus cotangent t times the denominator prime. But I like this function because the derivative is itself. The only thing I would do here is both terms are negative and both terms have e to t. So I would factor out negative e to t, and I would simplify with 1 from the denominator. And that would be it. I will not attempt anything else. So this will be a negative e to t, cosecant squared t plus cotangent t over e to t. It's up to you, either one. And then I will simplify one of these with one of the denominator, one factor in the denominator. So now negative stays outside, and cosecant squared t plus cotangent t over e to t. And that's the final simplified form. Any questions for me? Any questions?
Don't we need parentheses on top because the negatives distribute? So
No, because a negative in front of a fraction line will automatically be distributed to both. Same thing. So if you put negative in front here with parentheses, or you put negative in front of the fraction line, it would only be distributed to either top or bottom. We normally distribute to the top. Okay, so now finally, we can look at these limits with a different eye. Why? Because now we know L'Hopital's rule. So find the limit. They are not all these limits will be easier with L'Hopital's rule. That's for sure. Okay, so let's look at 46. We're asked to find the limit. Find the limit, or the limits if they exist, of course. 46. Limit as x approaches 0 from sine of x squared divided by x. What would you do with this situation? You will manipulate as much as possible, right? You will have x squared here. You need an x squared here. You will multiply and divide by x. Right? Am I allowed to do that? Yes, of course. I'm allowed to multiply and divide by x because it's still 1. If I multiply the top by x and the bottom by x, I didn't change anything. But now I know that this limit, as x squared, or x in other words, approaches 0. Well, I know that this limit is 1. Right, we discussed that. As long as this and this and this are the same, the limit would be 1. And of course, approaching 0, not 5 or anything else. The limit would be 1. So then, what will the answer be? When x approaches 0, all this is 1, but I have an x. It will be? Exactly. So this is a typical situation in which we applied this before, right? When all these three quantities were the same. So at this point, we cannot prove this with L'Hopital's rule. Why? Because this is a function, and inside of it is another function. So we will do this after I show you the chain rule. Okay? So let's look at another example, like 42. We have limit as theta approaches 0 from cosine theta minus 1 over sine theta. Okay, where does the top go to? The top goes to, very good, because this is 1 minus 1. Awesome. Where does the bottom go to? Okay, I like it. I don't have, in this situation, I don't need to manipulate algebraically this expression or function because I can use L'Hopital's rule in a situation of 0 over 0. What is the cosine prime? What cosine prime equals to?
Negative sine.
Excellent. What is the derivative of negative 1?
0.
Perfect. What is the derivative of sine?
So it's
Now, let me just make sure that you understand that we never differentiate a quotient like this, ever. We do this because it's inside of a limit. That's first condition. And second condition, because it's 0 over 0. Do not ever get confused and see a quotient and say, oh, I'm going to differentiate the top and differentiate the bottom. Don't do that, right? So this is a function inside the limit. And because we calculate the limit and it's 0 over 0 or infinity over infinity. So not to get confused. Okay, so now let's plug in again. So where does this go when theta approaches 0? Excellent. Where does this go when theta approaches 0? Excellent. And the answer is? That's it. Very good. So now we worked on this problem, this one, 48, some time ago, algebraically. But now you'll see it's much easier with L'Hopital's rule. Let's do that one more time and then continue with the chain rule. So this was 48. And tell me if you remember this. Sine x minus 1 over x squared plus x minus 2, of course, when x approaches 1. What did we do before?
plug in.
Yes, first of all, we have to plug in. Absolutely, yes. So 0 over 0. Yes, 0 over 0. No, let's write it. I completely agree. Perfect. So now, what did we do next?
Factor the-
Exactly, and then we showed which piece is going to 1. Let's not do that, because we've done that once. So since it's 0 over 0, function over function, I'm allowed to use L'Hopital's rule. What is it? Still have to use a chain rule. But I'm going to say what it is because I wrote it now. I don't want to erase it. So again, this is a function. If I had only x inside, it would have been sine x. That's it. But I have a function inside of sine, which is x minus 1. It happens that the derivative of this is still 1. And it's not going to make a difference. Okay? But otherwise, I would have not been able to use. If I had x squared here, I would have not been able to use general differentiation. I will have to use the chain, which I am going to, after this problem, I'm going to show you. So trust me, the derivative of the top is cosine x minus 1 times the inner function prime over, that's 1. What is the derivative of the denominator? Very good. Now let's plug in again. Where does the top go when x approaches 1? Exactly, because it's cosine 0. Excellent. Where does the denominator go when x approaches 1? Very good. So the answer is 1/3. Yes, please.
Could you substitute the sine into the x minus 1?
You can substitute it with something else, but then you have to substitute everything else. It's a very good idea. So you are saying something like this. Instead of x approaches 1, you will write x minus 1 approaches 0. You'll have x minus 1. You will have x plus 2 and x minus 1. So you want to substitute this by y, this by y, and this by y. But then you have to substitute this as well. Or not, and you will say, okay, this approaches 1. So where does this go when x approaches 1? Yes, so the answer is 1/3. I completely agree. You can always change the variable the way you like, but you cannot have two variables in the same function. So once you change this into into y, then you have to replace this x by y plus 1. But yes, I accept that. It's very good. Good. 3.4, the chain rule. Okay. So let's go back to x to the nth power. And you can say, what does this have to do with the chain rule? In a moment, you'll see. So when we want to differentiate x to the nth power, what do? We bring down n, we subtract 1 from the power, and we stop. The correct answer should be times x prime, times the inner function prime. But how much is x prime? Exactly. That's why we don't need to write it, because it's 1. Now, that's a preliminary idea. Second thing that I would like to say, if I have the square root of x cubed plus 1, can you please tell me which one is the so-called inner function and which one is the outer function? So before you answer, here's my question. So let me clarify this. We are given the square root of x cubed plus 1, and we're asked, evaluate this function when x is 2. Which piece of all this would you evaluate first? You cannot get to the square root. Oh no. You cannot evaluate the inside. If you don't evaluate first the inside, you're not going to apply the square root. You can't. You don't have the number to apply the square root to. So one more time. So I'm asked to evaluate this function for x equals 2. Which of the pieces I have to evaluate first? X cubed plus 1. You can say x cubed first and then add 1 and then the square root. I accept that too. So this will be the inner function that has to be evaluated first. And then when I'm done and I get 5, let's say 15, whatever, then I apply the square root to that number. So there is more than one correct answer, if that's what you want to say. So the inner function, we can consider this. We can consider x cubed and then x. It's better just to consider this the inner function, one function, and this is the outer. Why do I need this? This is function decomposition. The inner function is x cubed plus 1, and the outer function is the square root of x. Why do I need to even mention this before I talk about the chain rule? This is crucial for the chain rule, because we are going to differentiate something like this, and we have to differentiate the outer function first times the inner function prime. So let's start. I'll come back to this in a moment. I want to start with something even easier. So if I have 2x plus 1 to the 10th power, and this is my y, and I want to determine dy over dx. So I'm covering it. Imagine that it's just x to the 10th power. What would you write? Of course 10. Of course this quantity to which power? 9. But surprise, I don't have x. I have a function other than x. So I will write 10 indeed. I will write 2x plus 1 to the 9th, but now multiplied by this inner function prime, which is 2. Exactly what we should have done here. The reason why we didn't is because the derivative of the inner function is 1. So it turns out that the answer is 20, 2x plus 1 to the 9th power. Now the previous example, which is the cube root of x cubed plus 1, is the same idea. Let's differentiate this. Before we differentiate it, I would like you to understand that this is nothing else but this. So I replace the square root of x cubed plus 1 by x cubed plus 1, everything raised to 1/2. Why? Because the square root is power 1/2. In the same way we differentiated that function, we have to differentiate this one. We bring 1/2 in front. We subtract 1 from the power times the inner function prime. So 1/2 times x cubed plus 1. When I subtract from 1/2 1, what do I get? Very good. Times the inner function prime. How much is this prime? Very good, awesome. So simplified, 3x squared over 2, the square root of x cubed plus 1. And that is final. Okay, so let's talk about the chain rule. We already applied it. So f comp g, this is function composition. I hope you remember function composition. From f and g, which function is the outer, which function is the inner? G is the? Very good, awesome. Because this is f of g of x, where f is the outer and g is the inner. So here's the chain rule. When we differentiate f of g of x, we already used this. Can anyone tell me what to write? Remember, we differentiated the outer function first, and then we multiply by the inner function prime. F prime of, yes, you can write it like that as well, times g prime of x. And this is the chain rule. I would like us to choose problems to practice the chain rule. Ready? On page 205. In some situations, we will need to fully simplify the function. In others, don't even touch it because we can't. Okay, let's start with, yes, I would like to start with 10. In 10, we f of x, which is 1 over 1 plus secant x, everything squared. And you will say, well, it's a ratio, you have to apply the quotient rule. I will say yes, but no. Why? Because this is easier. To which power? Excellent. That's what I want to differentiate, not this. So let's write f prime. Can anyone dictate? Very good. Times 1 plus secant x to the, excellent, times secant prime, we just learned that, it's secant tangent. Secant x times tangent x. Don't touch anything. There is no need, and you can't. That's the only thing we can do. Let's look at a product, like 18, and then a quotient. Any questions on this? Let me stop for a moment. Please ask any questions you may have, anything that you would like to go back to. Anything? Anything? Yes, please. This was given in the problem. So it's -2. I copy the function, subtract 1 from the power, and I differentiate the inner function, which we just learned is secant times the power.
It's confusing.
Better?
It's probably
Other questions for me here? Other questions before we look at the product? Okay, so the product, I'm going to choose 18. If you want to choose another, let me know. Is 18 okay? Okay, in 18, we have g of x, x plus 1. No, I'm sorry. It's x squared plus 1 to the third power times x squared plus 2 to the sixth power. And you could say, I don't need the product rule. Just take this to the third power, take this to the sixth power. I will need 2 hours to do this. Say it again. 205. Sorry. Yeah, all from 205 for now. So this is the first function, and this is the second function. We couldn't differentiate this product last week because we needed the chain rule. Why do I need the chain rule? Because this is not plain x, and this is not plain x. So that's why we have to differentiate, including the inner function. Okay, so remember the product rule. I have to differentiate the first times the second plus the first times the second prime. Can anyone help with g prime of x? Yes, very good. Very good. Very good. So let's stop for a moment. All this is the first function prime. Excellent. Times the second function. X squared plus 2 to the sixth power. And now plus. I copy the first function, which is x squared plus 1 to the third. And now I reached the second function, but now I have to differentiate. Can anyone give us the answer for the second one?
6.
Yes? Times? Very good. Times? That's it. And you may say, okay, I'll stop here. Well, the answer we can't. We have to take it one more step. But before we do that, any questions for me? Any questions on this? Yes, go ahead.
Where's the 2x coming from?
The inner function prime. If this is x, then I don't need 2x, but it's not x. It's x squared plus 1, and I have to differentiate. The same thing here. X squared plus 2 is not just plain x. So I have to differentiate and I get 2x. Yes, Vanessa?
That first line, or the second line, I guess, the 3 times x squared plus 1, is this supposed to be cubed or just 2?
So x to the n power prime n x to n minus 1 times x prime. 3 times x squared plus 1 to 3 minus 1 times the inner function prime times the second function. And plus, I copy the first function. The power comes in front. I subtract 1 from the power times the inner function prime 2x. Better? Okay, so now I will rearrange these two terms one more time as 6x in front, x squared plus 1 squared, and x squared plus 2 to the sixth. And also plus 12x in front, x squared plus 1 to the third, and x squared plus 2 to the fifth. I'm sure you remember this from pre-calculus. And now I have two terms, and they have something in common. I need to pull that common factor or those common factors out. Can anyone give us the common factors of these two terms? This is one term, one product, and this is one term, one product. 6x. Good. Then, to which power? Yes, because 2 and 3, I choose the smallest. Good. Then also x squared plus 2, to which power? Very good. And now we open a bracket, and let's see what is left. As you see, 6x is completely out. This is completely out, but I have 6, and this is 5. So what is left from the first term inside the brackets? X squared plus 2. Now plus From 12x, I took out a 6x. So there is a 2 left inside. Then, from x squared plus 1 to the third, I took 2 of those out. But 1 is left in. And then all 5s are out. Okay, let's stop for a moment. Do we understand this step? Do we understand this step? Is that a yes? Yes? Right?
The x squared plus 2 to the fifth and x squared plus 1 to the second, I don't understand like why they go away.
They don't. So if I have x to the third plus x squared and I factor out x squared, they don't go away. They're here. X squared times x is this. X squared times this is this. It's the same process. This multiplied by this will give you this term. These multiplied by this will give you this term. It's the same process. They're not going away. We're just factoring them out. So see, this does not go away. I just factor it out from the other two.
I just don't understand why they are in brackets.
These?
The x squared plus 2 to the fifth and x squared plus 1 to the second.
Okay. So here's the reverse operation. 6x times this, times this, times this. It will give us 6x, x squared plus 1 squared times x squared plus 2 to the 6th power. Plus all this times this will give us 12x, x squared plus 1 cubed, x squared plus 2 to the 5th. So we factor out the common factor. From 3, we took out 2, so 1 is left. From 2, we took all of them out, so there's 1 left, just 1. Same idea, just that there's more to it because we have more factors. So they're not going away, they're just pulled in front. So you understand that 6x is in common to both terms.
Yeah.
You understand x squared plus 1 squared is common to both, not cubed, but squared.
Yes.
I have to choose the smallest power. I cannot choose 3. I have to choose 2. The smallest of the 2 is 2. The smallest of the 2 is 2. The smallest of the 2 is 5.
Okay.
So 6x is out, so I cannot write 6x in brackets. X squared plus 1 squared is out. I can no longer write x squared plus 1. But from these 6, I only took out 5, so I have to have 1 left over inside. And then I reach the plus. So from 12x, I took out 6x, but I only have a 2 left. From these 3, I took out only 2, so 1 of them has to be left inside. 1 second, Ricky. And all these 5 are out, so there is no more.
Okay.
Better? Yes, Ricky?
Why did you plus signs?
This one?
Like after the x squared plus 2 in the 6th power and before the 12x?
It's plus. It's the product rule. So the first prime times the second plus, that's the product rule. Plus the first one times the second prime. That's the product rule.
Because there's like 2 plus signs.
Oh.
Asking for the 2 plus signs in the
Right.
next
If I don't put something here, you may think that this is done. Right? So I put plus just not because it's 2 pluses, but to ask you or indicate that there is something follow. Because if I don't write anything, you may say, oh, this is it. But if I write the plus and you look for the next plus, which is basically the same one, but I have to break it into 2 parts. It's not plus plus. It just tells you there is something that follows. It's not done. Okay, so now we have to combine like terms here, x squared plus 2x squared plus 2. So the final simplified form is 6x, x squared plus 1 squared, x squared plus 2 to the 5th, and in parentheses we have 3x squared plus 4. And this is indeed final. A lot of trouble, yes. So from here, here. We have time to look at a ratio. And maybe something with e, or something with polynomials. Which one would you prefer? I do not consider section 3.4 finished, but I would like you to completely review everything we've done from 3.1 to 3.3. But as I said, I will choose homework in a minute. So would you prefer a ratio with e or without e for now? We will have to do both anyway. Without e, very good. It's a good starting point, I agree. Okay, so here it is, 26. G of y is a function, is a ratio, y minus 1 to the fourth, and y squared plus 2y to the fifth. Like before with the product, this is not an easy situation at all. It has a lot of steps, and of course, it ends with simplification. So g prime of y. Let's write the denominator, and please give me the denominator of the derivative. What would the denominator be?
Y squared plus 2y to the 10.
Excellent. Thank you, Britt. Excellent. Indeed. Now let's differentiate the top. We bring down 4, we subtract 1 from the power, and we multiply by the inner function prime. But y minus 1 prime is, right? The derivative of y is 1, the derivative of negative 1 is 0. So there is nothing, I don't need to write anything. So y squared plus 2y to the fifth minus, I copy y minus 1 to the fourth, but now I have to differentiate the denominator. I will bring 5 in front, I will subtract 1 from the power, but I will have to differentiate the inside. What is the derivative of the inside?
2y.
Plus 2, very good. So then I have, I will not have enough room, so I'm going to put an arrow. So 5y squared plus 2y to the fourth times 2y plus 2. I'm going to write it one more time because it's not clear at all. G prime of y, 4, y minus 1 cubed, y squared plus 2y to the fifth, minus y minus 1 to the fourth, times 5, times y squared plus 2y to the fourth, times 2y plus 2, with parenthesis, y squared plus 2y to the 10th. And you can say this is a mess, and I will have to agree. However, we will clean it up. And please tell me, what should we factor out from the two terms in the numerator?
Y squared plus 2y to the 10.
To the fourth, excellent. And also y minus 1 to which power? Very good. And you said y squared plus 2y to the fourth. Open a bracket. And let's see what is left. So we took all these 3 out and 4 of the 5 out, but there is a 4 in front. Can anyone tell us what to write? 4 indeed. What else? Very good. And now we reach the minus. Let's see what is left here. So all these, no, 1 is left from y minus 1. This is completely out. So one of this, the 5, and the 2y plus 2. So the 5, y minus 1, and 2y plus 2. Let's stop for a moment. Is this clear? Brayden, do you feel better with this now?
Yes.
Okay. Is this clear, everyone? Everyone? Okay. So of course, I'm going to do this right away to get it out of the way. Why? This is a factor. This is a factor. I can do that. Only now I can. And now the next step would be y minus 1 to the third. I have to simplify in the brackets. And that will be final. We still have time? Yes. 1 minute. So, please finish it up. I just want to select a couple of problems for you to do. Help me in the meantime by finishing it up. So here's your homework for Thursday. 22 on page 181. 35 on 182. 24 on page 189. Oh, I'm sorry, you can do 23. I know you like to check the answer, I'm sorry. And you can do 21 here. Sorry about that. Okay, 31 on 189. 13 on 197. And 45 on 198. I'm not going to sign the chain rule just yet. Yes, 21, 181, 35, 182, 23, 189, 31, 189, 13, 197, and 45, 198.